Hi everyone. I am going to talk about my recent work, which was done with Rishi Khatri and Tuhin Roy at TIFR. Okay, so let me begin. If dark matter has a particle nature, then one of the detection strategies is indirect dark matter searches, but these have mainly focused on emission signatures. So if you have dark matter, that dark matter can decay or annihilate, and it is possible that we find these extra standard model particles, which could be a dark matter signature. But till now, the less traveled path that we have taken is the absorption signature. So it is possible that dark matter leaves its imprints as absorption signature. So this is something which has not been explored much, and I will try to convince you that it is very promising. So the main idea is that if we have a background source and we have dark matter, which has a small coupling to photons, then dark matter can absorb photons from this background source, which will result in an absorption line. And I'm going to talk about two kinds of sources. So one will be the isotropic CMB, which I'll connect to the edges signal. And the other is when we have a compact source like a quasar, which gives dark forest. So without going into the details of the model, the simple things that we need to do the physics of absorption lines is that we have a dark matter particle which has two states. First is the ground state and the excited state with some energy splitting, which can be expressed in terms of temperature as T star. And dark matter is going to populate both of these states, which is going to be characterized by the excitation temperature, by this Boltzmann distribution. Now, the transitions that can take place in this two-level system are of two kinds. So one is because this talks to photons, so we'll have electromagnetic transitions, which could be absorption or stimulated or spontaneous emission, which can be parameterized in terms of Einstein coefficients. And the other is dark matter can also have inelastic collisions where two particles collide and one of them get excited or de-excited. So when we put this picture into our universe where we have CMB and we have dark matter, which are two systems at two different temperatures, then these two systems talk to one another through these two-level transitions. So one is the radiative transition that I talked. So if CMB photons are more in number or these processes dominate, then this population level is going to be decided by the CMB temperature. And if dark matter collisions dominate, then this temperature will be decided by the dark matter temperature. So now, so this is a timeline. So if this is basically I'm plotting different temperatures, CMB, dark matter, and excitation as a function of redshift. So when dark matter decouples, so the dark matter temperature falls from the CMB temperature. And at these high redshifts, inelastic collisions are strong. So excitation temperature is going to be equal to the dark matter temperature. So when CMB is going to pass through these dark matter particles, since the temperature is lower, we will see an absorption. So you can see when collisions dominate, we start seeing an absorption signature. So basically, this is the CMB spectrum with respect to perfect black body. If it is horizontal, it's perfect black body, but because it's going down, it's going into absorption. Now, as the number density of dark matter falls, radiative transitions start dominating. And then this excitation temperature goes to CMB temperature. So when this medium and the source have the same temperature, then this absorption signal vanishes. But this will be the story if we just have dark matter and CMB. But we also have baryons. And these are very important in establishing the black body spectrum of CMB. So I think this was talked about by Mayuri. So at different epochs, different processes dominate. So we have Bremsstrahlung and double Compton scattering, which are photon number changing processes, and we have Compton scattering. So these are important in establishing the black body spectrum. So here I'm showing the black signal, which I showed you earlier, where we just had dark matter and CMB. And now we are including this Bremsstrahlung process. So Bremsstrahlung is something which is important before recombination when universe is ionized. So you have lots of electrons and ions, and they can scatter and they can create photons which will erase this distortion from CMB. So we are then left with a small window where we can have an absorption signal. But this is something which is a function of CMB, the frequency that dark matter is absorbing. So now, so I think this is So edges collaboration observed an absorption signal in the CMB, which cannot be explained by the standard 21 centimeter cosmology. So one of the solutions that we gave was that it could be dark matter, which is showing its signature as this absorption line. So this is like two choices of model parameters, which can produce the amplitude and the width. But of course, as discussed, there is still no consensus on whether edges is the correct signal, because Saras ruled it out. So this feature is something which can occur in any part of the electromagnetic spectrum. And so here I'm just showing that if we change the splitting between the two energy levels, the signal changes. And it is also a function of what these collisional coupling of dark matter would be. So if the temperature dependence is steeper, then the signal becomes more steep. And it also depends on coupling to photons. So if the coupling is stronger, then the signal will vanish quicker. So this is what happens when you have CMB, but we also have compact sources. So if we have quasar at a high redshift, and there is a dark matter halo on its way, which is intersected at an impact parameter P, then all the dark matter particles along this line of sight can absorb photons from the quasar. So that is something which is expressed in terms of optical depth. So it is proportional to the coupling of dark matter to photons, also number density of dark matter particles along the way. And again, the excitation temperature, which decides the population of dark matter particles in the two states. And also the Doppler line profile. So if particles are moving along the line of sight or away from the line of sight, that brings a spread in the absorption signal. So here we take two extreme scenarios. One is we consider dark matter to be collisionless. So there is no inelastic collision, and we just have CMB as our background source. So this excitation temperature is equal to CMB for collisionless case. And if it is collisional, then excitation temperature is equal to the temperature of the halo, which is basically coming from gravitational interactions. So now this is some properties of the halo that I'm showing. So here I've plotted the temperature of halo of different masses, comparing it with CMB. So if the temperature is, if the halo mass is below 10 to the 8, then CMB temperature is above the halo temperature. And the number density of dark matter for a given halo mass increases with redshift. So that has signatures in the absorption lines. So this is this is like absorption line for a given halo of different masses at redshift 5 intersected at 0.5 R virial. So just to remind, so the amplitude, so this is an absorption line with some amplitude and a width, and amplitude is decided by this excitation temperature, ratio of particles in the ground state or excited state, and width is decided by the temperature of halo. So what we find here is that in case of collisional dark matter, so in case of collisionless dark matter, there is more absorption when we increase the mass, which is basically happening because number density of dark matter particles is increasing. But in collisional dark matter, the excitation temperature is important, and that increases with the halo mass. So you have less particles in the ground state. So the signal is weaker for bigger mass halo. Now, this was what happens when you have single dark matter halo, but you can have multiple dark matter halos along the way. And each of these dark matter halo will absorb photons in its rest frame at a fixed frequency, but due to expansion of our universe, this is going to redshift, and we will today see it as many absorption lines, which is like the dark forest, something similar to 21 centimeter forest for hydrogen. So what we did was, so this is like a collection of absorption lines, each line characterized by a amplitude and a width. So we just plotted, we just counted how many lines correspond to a particular amplitude for two cases of two natures of dark matter, collisionless and collisional. And we found that the absorption is stronger in case of collisional dark matter compared to collisionless. And the other was, we also set a minimum halo mass. And we found that as we decrease the minimum halo mass, we intersect more halos. So there is more number of counts if we decrease M minimum. And the other was about the line width. So if we decrease the minimum halo mass, or we make us like the cutoff in the power spectrum is smaller, then you have much more halos of smaller masses. So they have smaller temperatures. So this extends to lower values of line width. And this is something about the detectability. So here I've plotted the different experiments which measure the spectra of different sources in the full electromagnetic spectrum, ranging from radios to X-rays. And so to detect these lines, we require that the width that each of these experiments is measuring should be smaller than the width of the absorption line we are getting from dark matter halo. So that is around 10 to the minus 3. So these optical and radio wave band experiments can actually be sensitive to these kinds of signatures. And the other was that if this is a potential explanation for edge signal, then this will all correspondingly have a dark forest in 20 to 40 gigahertz range for a source at redshift 4. So this is the VLA band, very large array band, which is in this frequency band. So if we are able to find something here, then we will be able to confirm or reject this kind of model. And so then, like, I only talked about the observational features. Now the question is, what kind of dark matter model can give rise to this signature? So one of the proof of principle models that we came up with was that dark matter is a composite state made of two particles. Now, since it has to interact with photons, it has small electric charge, but both are positive and negative. So two particles with equal and opposite charges. So overall electromagnetically neutral. But since dark matter has to be stable, so we introduce strong interactions. So these are like two dark quarks with small charges and strong interactions. And the transition happen in the hyperfine splitting. So basically two quarks with spin half anti-aligned or aligned. So I will just conclude now. So we proposed unique signatures of dark matter as absorption lines, which can give rise to a global absorption feature in CMB or spectral distortions in CMB, or it could give rise to dark forest in the spectrum of a quasar. And there is already a lot of data, and we can try to look for signatures there. Thank you.